Hi my dear friends, and welcome back to the Informatics 2 class, and we're going to start now lesson number 15. In this lesson we're going to continue talking about queues, the topic of the last two lessons. In this presentation we're going to continue in the basic operations on queues, and then we're going to talk about the implementation of the queues. We have started this topic actually in lesson 14, and we have introduced the basic operations we're going to perform on queues, and then we hinted on the implementation of the queues. So we're going to just continue from where we ended last time we met. Okay, let's start with the implementation, and basically this is a continuation from where we ended last time. Basically in C, to get the next element in an array, we increase the index by 1. And that's basically the way we access arrays. So if this is my array, okay, and then these are the entries in my array, then of course if I'm at any position in this array, let's say position I, then to go to the next item, to the next entry in this array, I would simply just increment this, and then the index for this position is simply I plus 1, and that's what it says in here. However, if you all remember, as we said last time, this way of implementing the queue is not going to be very helpful, because I'm going to have the problem of going at the end and having empty spaces in here that will never be used again, because simply the two major pointers that we use to implement the front and rear of the queue are basically going to be incremented the whole time, and they will never be decremented, if you all remember. And that means after several appends and services along the road, then I'm going to end up with a wasted space in here that will not be used. So if you all remember, we said instead of doing implementing the queues in a flat straight array, we introduced the concept of circular array. Okay, and that's what we want to talk about in here, and we're going to see how to manipulate the indices when we're talking about the circular arrays. So for circular array, to get the next element, we don't always go I plus 1, but rather it depends upon the situation or the position we're at the moment. So the circular array conceptually looks like this. And actually, this is entry number 0, and this is number 1, 2, and so forth, around this donut till I get to the last entry. Okay, so basically this is entry number 0, index number 0, 1, 2, and so forth, and this is the very last, which is n minus 1, assuming that I have n entries in here. Okay, so that's okay if we're along the road in here to where you can go to this position by incrementing the index by 1, but when I get to this position, okay, I'm not going to go straight to m plus to this position plus 1, all right, because that does not exist physically among or within my array. So instead of that, we're going to do something like this. So I need to check whether I'm at this border or I'm in the middle of my array. So instead of just saying I equals I plus 1 to increment and go to the next position, we're going to do something like this. If I is greater than or equal to max minus 1, and that's this position in here, then in that case, the next position to me is actually to go to 0 and to circulate again. So basically what we're saying in here, if I reach that limit, then I equals to 0. And that means go to this position again, circulate again. Otherwise, if you're anywhere in the middle of your array, you just simply increment your index. Okay, so it's a simple way of doing it. Okay, it's physically, it's straight inside the memory. It's like a flat array like this one. However, conceptually, by doing calculation like this, actually we're making it looking like a donut or a ring like that. So that's the concept of the circular array then. Well, I can do it this way, or there's another way of implementing or saying the same thing in here, and that's by using the modulo function. And I think you all know the modulo function. We have talked about it the other time. The syntax for the modulo function is this percentage sign. And basically what we're saying in here is that the new index is simply I plus 1, so I'm incrementing 1, but don't absolutely increment that, but rather make a modulo to max, and that max is the maximum number of entries I have in my array, in this case n. So this is a modulo n kind of function. Okay? So I will increment the position I, okay? And if the number I get after the increment is within this scope, then it's gonna just keep it, all right? Otherwise, it is gonna divide it by n and take the remainder. So basically, assume that n is simply 8, the same example we gave the other time. So I have 8 positions in here, numbered from 0, 1 to 7, okay? And I'm filling my array, and assume that the current I is here, and that's I'm at the last positions, and I would like next to go to this position. So the calculation I'm going to do is basically I'm going to say I plus 1, and I'm attempting to go I plus 1 equals to 8, okay? And there's no index 8 in this array. So what I'm going to do after I increment, I'm checking in here the first way of implementing it. Is I greater than the max? Yes, it is. Well, in that case, just make it equal to 0. So instead of putting 8 in there, what I'm going to put is 0, and that means go down here. That's the first way of implementing this circular array. Or I would say something like modulo max. And the max that I have is actually the 8. So what I'm going to take this I plus 1, divide it by the max, which is 8 in our case, n. Okay, and I'm going to take the remainder. So this is 8 divided by 8, that equals to 1, and the remainder is 0. So quotient equals to 1, however, the remainder is 0, and I'm going to take my remainder as the index within the array. So either this implementation or that implementation works, and they both make my array structure kind of circular rather than straight. Okay, let's look at the boundary conditions, and we mean by the boundary conditions to where at the borders of this array. Let's see how rear and front behave as we move on, filling, appending, and servicing. Well, here is an illustration. In this picture, green indicates that the entries are empty. Blue indicates that I have a valid entry in there. Okay, so in this particular example here, the queue contains one item. And in that case, rear and front are pointing to that entry. Okay? And now, after this, I'm going to serve. Serve means remove an entry, an item from the queue. All right? And when I'm going to serve, then whatever entry pointed by front is going to be taken out of the queue. Okay? So I take it out, and then I'm going to adjust front accordingly. So based on that, that's the situation. The whole queue is now empty. However, front is pointing here now to the next position. Okay, and let's say I continued with that, and in this situation in here, okay, I kept going, filling actually the array with the with entries as they come appending, and this situation here shows that the my queue is almost full. I only have one empty slot in the queue, and rear is pointing to the very last entry I added. Front is pointing to the first entry to be served. So this is the situation that we have in here. Okay, and down here a new entry comes, so I'm gonna append it to my queue. So basically I'm gonna add it here, and then I'm gonna adjust rear accordingly. Well, what does it say? Very simple, straightforward. We all understand this. However, look at this situation in here and this situation in here. Both rear and front, they're pointing to the same locations. However, the entire queue is empty here to where it's full here. So how would I know whether my queue is full or empty? In both cases, as we can see in the example here, in both cases, the difference between front and rear is one position. So when I look at front and rear, and I see that the difference is only one, does that mean the queue is full or the queue is empty? Well, I can never tell, actually, from the situation. How to tell whether a queue is full or empty using the indices front and rear? There's no way, simply, according to what we have on the previous slide. When full, front equals to rear plus 1, and when empty, again, front equals rear plus 1. Same thing. So sad. Well, I have to tell, because that's very crucial. I mean, you have so many entries in the queue. Why would you assume it's empty, or vice versa? You know? So we got to find a way to solve this little problem we're having in here. Okay, let's look at the possible solutions. Well, there are so many ways of going around this problem, actually. Well, the first proposed solution in here is to insist on leaving one empty position in the array. So you will consider, in this case, your array to be, or your queue to be full if it has so many entries, but we have one that's always kept blank, kept empty. That way, I'm gonna always, when it's full, I'm gonna have front and rear pointing like this. Rear and front. And I will never allow an entry to get to this. That means if the size of my queue is n, then the maximum number of entries I can have is actually n minus 1. This is a possible way of doing it. So when it's empty, then both front and rear are going to be pointing here, and the difference between them is just 1. However, when the queue is full, the difference now is 2. And that way I can distinguish between a full queue and an empty queue. That's one way of doing it. It's possible. However, if I do it this way, I'm losing one position in my queue. Is this a big deal? Well, it all depends upon the application, actually, and it depends the amount of memory I'm reserving in here for that entry, which is going to be kept free or empty. And I cannot put any entries in there. If this space is actually very large, then I'm afraid the solution is not the best solution to think about. Okay? But if the records that I'm going to place in the queue are of reasonable size, so then it doesn't hurt if I keep one, if I insist on keeping one of them empty the whole time, just to solve the problem I'm having with full and empty queues. Okay, so that's a possible solution, and some people use that. According to this, the queue is considered full when rear has moved within 2 positions from front, and that's the scenario we have showed in this illustration here. Another way of doing it, however, is to use an integer in my queue structure in the definition of the queue. And that integer basically carries always the number of entries I have in the queue. All right? So basically, in my queue structure, according to the structure we defined the other time, we said that it's going to have basically 2 pointers, one called front and one called rear, and then a pointer to the entry. Okay, whatever types in here. Of course, these are integers because they're basically indices within an array. Well, and entry contains the actual data the user is going to enter in the queue. Well, what we can add is simply another integer in here called count, and basically each time I insert a new entry, I increment this by 1. Each time I serve, I will decrement this by 1. So this keeps track of the size of the queue. Okay? And actually, this is not a big deal of addition in terms of space, because I'm just reserving one extra location in every record, which is 4 bytes long, just to give me always the number of entries that I have in the queue. And this is very simple. In this case, I don't have to worry about leaving an empty space in the queue, but rather I can always check whether the queue is full or empty by looking at this number. If this number is 0, that means the queue is empty. If it is n-1, then the queue is full, regardless of the position of front and rear. So in that way, I can solve the problem that I had without worrying about leaving space. So especially when the records that I have in here are too huge, so it's more economical to add this one in here, rather than leaving a huge space, an empty space in the queue. Actually, in our implementation, we're going to implement this solution. So this is the adopted solution in our case. However, there is a third possibility for solving this problem, and that is set one or both indices to some value or values that would otherwise never occur to indicate an empty queue or a full queue. Well, like what? Well, basically, I know that the valid indices range from 0 to max -1. So if this is my queue, I know that the possible legitimate indices are 0, 1 up to max -1 or n-1, the way we used to deal with it. Okay, so I will never have something like -1 as an index. True? So if that is the case, how about if I use this as a flag when the queue is empty? Okay, so I don't put a 0 in there, okay, but rather I would put a -1 to indicate that the queue is empty. And that way, when I do like front minus rear, it's going to be different from having front minus rear in the case of full from that when the queue is empty. So what we're going to do is something like this. I could put these kind of flags for both the full case and the empty case, or just for one of them. The idea is just to distinguish between the two situations, the full case and the empty case. So what we're saying in here, if array entries are indexed from 0 to max -1, and that's what we have in here, then an empty queue could be indicated by setting rear equals to -1 rather than having its actual value. That way, when I subtract, I get some different value from the 1, which actually represents the actual case. So if I have in the middle of it front and rear like that, and I know the actual physical difference is 1, okay, and that's where I had the problem of full and empty. So if I do it this way and I put rear in this case equals to -1, then the difference is going to be some large number, and that tells me that the queue is empty. So it's not an actual size of the queue, but rather it's just a flag to tell that the queue is empty in this case. And the solution is adopted as well by many programmers. Okay, so these are basically the 3 different solutions one could think of to solve the problem of distinguishing between situations where I have a full queue or an empty queue. Okay, as I said, we're going to adopt solution number 2, to where I'm just going to add in the structure of the queue an integer entry called count, and that basically is going to tell me always the number of entries that I have in the queue so far. Okay, and based on this, we're going to redefine the structure for the queue. So struct queue integer count, and this is the addition we have in here. And we have the traditional front and rear indices, of course, of type integer. And then the max queue, which gives me the maximum number of entries I could have. And this refers to the fixed structure that I have for the queue. And then of type queue entry. And this is basically the structure which refers to the entries in the queue. We used to call it entry. It doesn't matter. It's just a pointer to a structure where I'm going to have my data, which I'm going to insert in the queue. And this structure is going to be called queue. So I'm going to refer to this later on in our implementation. Okay. Based on this implementation and this definition of the queue, let's now start developing the functions for the different prototypes that we have introduced last time. The first function we want to talk about in here is to create a queue. Well, to create a queue, I don't need any prerequisite for this function, as we mentioned earlier. And as a result of this, the queue, which is called the queue, will be created and initialized to be empty. And again, in here, since we have learned and we have introduced the concept of dynamic allocation, okay, we're not going to be using the static allocation, static array, and then change it later on the same way we did with the stacks. We're going to go right away to the efficient way of building our structures, and that's using the malloc and free functions. And that's what we're going to use in here. So basically, create queue basically takes a pointer to the queue which I'm going to create, and takes an integer called max elements, and that refers to the maximum number of entries I could have in my queue. Okay, the way I'm going to start after this is by creating a space, allocating a space of size q, okay, and return that, make it point to my queue actually in here. And that basically creates the big container, just a pointer, as a matter of fact, 4-byte pointer in here, which is going to be called the queue. And later on, this pointer, when I successfully manage to allocate this location in the memory, I'm going to make it point to the big structure here. So I'm creating this pointer now. Okay, so basically, I'm going to use this malloc size of queue of type to point to a structure called queue, the one we introduced in the previous page, and cast the return value instead of void to point to this kind of structure. Well, I don't know if this operation is going to be successful or not. Okay, if it's not successful, that means the operating system could not find enough space in the memory to do that, then it's going to return null. So I need to check to see if this operation was successful or not. So what I'm saying in here, if q does not equal to null, that means the data structure has been created. The head of this structure has been created successfully. Then after that, I need to allocate now this space for the whole storage. So what I'm going to do now is allocate the space for the queue. So what I'm going to say, a Q array, referring to the entries in here, I'm going to allocate now in the memory enough space to accommodate all elements, maximum number of elements. So what I'm saying in here, malloc, maximum elements times the size of each element, number of bytes. So I'm reserving a number of elements, like let's say 100 elements. Each one of them has the size of queue entry. All right? And so allocate memory for that and make the return value of this type, a pointer of this type, so this refers to it or points to it. So I'm making this actually to point to this big structure if I manage to allocate it. Okay, so then it's two steps actually. First, I have to allocate a pointer to the structure of the queue. And then once successful, I need to allocate enough space with the size, maximum size of interest that I could have in there. Okay, and then initialize now the queue. Queue arrow count equals to 0, it's empty. Front equals 0 and rear equals -1, and that's the beginning actually to indicate that the queue is empty, and we started from -1 just to keep the logic correct so that always front or rear differ by 1 when the queue is empty. And make max queue equals to maximum number of elements. So I'm building the structure of the queue, which I had in there. Count, front, rear, max elements, and of course these items, which I'm going to fill later on. At least I'm just making space for them. Okay? And then just return. Well, this return, I'm going to come here either through all of these steps after successful allocation from the very beginning for this, or if I fail to do this, then Q in that case is going to be null. So if I successfully manage to allocate the memory, then I'm going to return a pointer which points to this whole structure now. All right? But if I fail, then the return value in here is just going to be null. Okay? So that's basically the create queue function. Very simple, very straightforward. Creation, allocation of memory, dynamic allocation of memory, and successful return with a pointer to that. Of course, with initialization in here. Okay, the second function we want to talk about. The queue is there, already created, and it could have some entries inside it. And I want to check now whether the queue is empty or not. And again, remember that the solution we adopted is number 2, to where I have this entry called count, which always tells me the number of entries that I have. Okay, let's see. So this returns, this function queue empty, returns a non-zero value, 1, if the queue is not empty. The queue, the prerequisite for this, queue has been created and it has been initialized already. And as a result, the function returns non-zero if the queue is empty, that's true, and 0 otherwise. So basically, this function is going to be of type Boolean, which going to return true or false, yes or no, 1 or 0. And it's going to take as an argument a pointer to the queue structure. Okay. What does it do? Well, simply, I'm not going to go through the entries asking them, are you full, are you empty, one after the other till I go through everything. And again, I'm not going to check the position of rear and front, but rather, according to the adopted solution, simply, I'm just going to go to the structure of this queue. One of the elements in here is called count, and that always gives me a report on the number of entries that I have inside the queue. So if this number is 0, then definitely the queue is empty, and I will return a yes. Otherwise, if that count is a non-zero value, then your queue is not empty, and you're going to return a false, a 0. So basically, the only statement I'm having in this function is simply this. I look at queue arrow count. Does it equal to 0 or less than 0? If that is the case, then this expression is going to return yes. And in that case, I'm going to have a value of 1. Otherwise, it's going to be a false or a 0. Same thing for the queue full. Very simple. What I'm going to do, it's again of type Boolean. It's just going to tell me whether the queue is really full and there is no more space to append. Okay? So basically, I'm just going to check this count again against the maximum number of entries that I have. So what I'm saying in here in the return value, a logical expression again, is count greater than or equal to max queue? If it is this much, then my queue is really full, and in that case I'm going to return a true value, a 1. Otherwise I'm going to return a 0. Very simple, straightforward. And adopting this solution actually made these functions very simple to develop. Let's look at the append. Append is where you need to add a new entry to the queue. Okay? And remember, we're going to be adding from rare. So the prerequisite for this is that the queue has been created and it's not full. So I have to check first to verify that there is a place inside the queue to insert this new customer. As a result, the entry, which is called item, is stored successfully as the last entry in the queue. Let's see how we're going to develop this. It's going to take 2 entries, the item which I need to insert and the structure of the queue, pointer to that queue. So the first thing I'm going to do is to check if the queue is full. Is the queue full? If yes, then there is an error. I cannot insert that entry. I'm sorry. Otherwise, I will first increment the number of entries in there because there is a new customer. And then I'm making rare equals to rare plus 1. Rare always points to the last full entry. So I have to advance it first and then insert the entry. So I'm doing this. Increment your rare counter. However, you don't increment and just increment because we're talking about a circular thing. So we're doing this modulo function here with the maximum number of entries. So basically, this statement says go to the next available entry and then place item at that location and return. Very simple and very basic. Serve. Serve. Now I'm gonna retrieve the entry pointed by front, all right, for servicing. All right. So the number of entries are gonna be less by 1 after this operation. Okay. So what I'm gonna do in here is simply the function is called serve. It takes as inputs a pointer to item, and it's passed by pointer in here because I'm going to change its value as it's going to contain after return the whatever entry I have on top of the queue, and then the queue itself. Okay, before I can retrieve, I have to check whether the queue is empty. So what I'm saying in here, is queue empty? If that is the case, then sorry, there is an error. I cannot serve anybody. Okay, the queue is empty. Otherwise, well, okay, decrement the counter in here, indicating that you're going to have 1 less item, and then put in memory, pointed by item, whatever entry you have, because front is pointing to a full entry. So take the entry in there, and then after that, adjust your front. Advance it by 1 to point to the next entry. And again, we're doing the modulo thing to implement this circular array, the structure which we talked about earlier. Queue size. Well, basically, the queue size is contained in count now. So anytime I would like to know how many entries are there inside the queue, you will simply go to the queue structure and look at count. So basically, what I'm doing in here, it's going to have a return value of type integer, and that reflects the number of entries I have in the queue. And it takes as an input a pointer to this structure, to my queue. Okay, and the only thing I'm going to do there is basically go to the structure defining the queue and just return count. Very simple, straightforward. So take queue arrow count, return it as your return value. Okay, so the values in here could range from 0, nothing, empty, to max minus 1, the maximum number of elements I could have. Okay, or anything, of course, in between. Very simple and straightforward function. Okay, so we implemented the create, append, serve. Is it full? Is it empty? Okay, and this last thing, the size. Well, what's left is how to traverse the queue. Well, the same thing we did with the case of stacks. I'm going to keep this as an exercise for you. It's very simple, straightforward. Basically, you're going to pass to this function the queue itself and whatever function operation you're going to perform on the entries in there. And basically, you're going to start from the very first entry pointed by front to the very last entry. Okay, each time you visit an entry, you're going to perform some kind of operation on that. So I'll leave that for you. And I hope you're going to enjoy it. The array implementation. Well, here is the structure actually which we defined in here, which basically contains many entries inside it. There is an entry of type integer that basically gonna contain always the number of entries in my queue. This is my actual queue, and this is just the structure of the pointer pointing to the queue. But I don't have just the pointer to the queue, but rather I have other information relevant to the queue. This information was, as you remember, the count, which tells the number of entries I have in there, the index front, okay, and in this case, this is my queue in this example, and I have 4 entries inside it. Front is pointing here. The index of this one is actually 1, so I'm having 1 in here. And the index here is 4, okay, so what I have in rear is 4, okay? And the maximum number of entries is actually the number of entries I have in here, and it's 9 in this example. And then in here, I have a pointer that points to this structure down here. So that's how we're implementing this basic queue. It's very simple, very straightforward. So anytime I want to retrieve any information about the queue as a whole, I refer to this structure in terms of where's the position of front, where is rear, and how many entries I have in there, and so forth. However, if I want to access the actual entries in the queue, then this is the actual queue, as a matter of fact. This is an info thing about the queue. All right? So I would just want you to distinguish between the two structures we're talking about in here. How do we work with the queues? The way we implemented the queues in here is using arrays. Yes, circular arrays, but basically they're arrays. All right? Can we implement the queues in a different structures? Yes, of course, maybe. We're going to see other ways of implementing that. Actually, what matters to us when we develop functions to work on queues, like is queue empty, full, append, serve, whatever, what we need to know is the concept of queues. So we know the conceptual idea of a queue, appending and retrieving or serving. We can use a set of operations defined on the queue based on that conceptual idea. But I don't really care how physically that queue was implemented inside the memory. In an array, the way we described it, with whatever structures we already defined, or in any different way. As long as that structure actually obeys the rule, the conceptual rules for queues, I can live with it. Okay? So what I care about is the basic idea of the queue. I don't care much about the actual physical presentation of that. Okay? What I care about is when I perform any kind of operation on the queue, that kind of operation is going to be performed in the way it should be, like appending goes to rear, serving goes from front, and so forth. Okay? So basically, when we talk about abstract data types, we don't care about the physical implementation, but rather we care about the physical, the conceptual actually implementation. So we know the conceptual idea of a data type. Okay? We can work with objects, and now I refer to objects rather than to the physical implementation of this type, rather than using a set of predefined operations. So basically, whatever inside the memory, to me it looks like just a cloud, something inside there, okay? But that's something actually obeys the general basic rules for the data type or the data structure we're talking about. So basically, I'm at an upper layer in here, and I develop my functions here to work on this thing, okay, in the conceptual way, without really caring about the details of what I have inside that structure. We do not really care and even know sometimes about how physically that data structure is implemented. We work with objects rather than physical things. Implementation can be changed. At any time, the implementation here physically can be changed because I find another more efficient way of doing it. Yes, you can do that. There is no problem with it as long as the interface between this physical implementation and this application in here stays the same. I mean by that, as long as the basic definition of the operations stay the same, then I can have anything inside here. It's transparent to me, and I look at it as a container that contains my physical data. So that's where when we say implementation could be changed, not even a bit in the application program will be changed. Different implementations are possible, and we're going to see some of these different implementations later on as we move on with this course. Well, thank you very much. That's all I want to talk about in queues. Hope you liked it. And of course, if you would like to refer to this material and other supplementary material, you go to the internet, to the UNINETTUno website, click on the Midnet U, and you're going to find lots of interesting stuff. Thank you very much, and I'll see you later.